Guys, today we are back with another problem, and today's problem is finding the shortest path in a weighted undirected graph. Okay, so how we are going to find the shortest path in a weighted undirected graph? So while we can see that we will be given a graph, okay, weighted undirected graph having n vertices numbered from 1 to n, okay, along with m edges, along with their weights. The shortest path between vertex 1 and n. We have to find the shortest path. We have to find the shortest path between between 1 to n. Okay, so I'm going to quickly increase the font a little bit. Yeah, so what we can see is 1 to n, along the find the shortest path between 1 to n. If there exists a path, and return a list of integers whose first element is the weight of the path and the rest consist of the nodes on that path. If no path exists, then return a list containing a single element as -1. So in this case, what we can see is we'll be getting a single element as -1 if there is no shortest path possible. Okay, so I'm going to quickly draw the graph before we proceed to our problem statement. Okay, so what we can see is initially we will be having some coordinates 1, 2. Okay, we will be having a coordinate 4. Okay, we'll be having a coordinate 3. We'll be having 6. We'll be having 6. So now there will be some edge weights and some distances as well. So if I just write the distances as 2, 5, 4, 1 and 3, 1. Okay, now I'm going to write the adjacency list. So the adjacency list will be list. If I declare there are a total of 5 nodes, we can see 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5. Let me just yeah, this is going to be my fifth value. This is going to be my fifth value. So in this particular case, what I'm going to do is I'm going to write the adjacency list. So the list will be like for 5 nodes 1, 2, 3, 4 and 5. Okay, and 5. So in case 2 and 2, 1 and 4, 2 and 2, 1 and 4. Okay, and similarly what we can see is 2 and 1, 2 and 3, 2 and 1, 2 and 3 and 2 and 1, sorry, it will be 4 and 3 for the node, because 2 is connected to 1 and 2 and 3. So 2 and 1, 2 and 3 and 5 and 5. Yeah, so I think this is not 4 and 3, this will be 2 and 3 only. So it was okay, 2 and 3 and 5 and 5. Okay, let's come to the third one. So for third one, on node 3, what we have the relations as 5, 2 and 4, right? So 3 is connected to 4. Okay, so 3 comma 4 and 4, and we will have a distance 1 and 5. 3 is connected to 1 and 5. This adjacency list as 4 and 2, 4 and 2, 1 and 5. And for 4 we will have values 1 and 1, 3 and 3, 5, 2, 1, 3, and most probably this is 4 and 3. Okay, so now we will be having a distance array. So the distance array will be initially containing all the values. Okay, so from 0, 1, 2, 3, 4 and 5. 3, 4 and 5. Okay, and they will be initialized with infinity to have a larger memory. Okay, now based on my traversal, I'm going to decide which value to assign to where. Okay, based on the priority queue, we'll be also having a priority queue. Okay, so let's imagine this is my, say, priority queue. Okay, this is my priority queue. So the bottom of the queue, what I will be having is I will be having a value 0, 1, 0, 1. Okay, now when I'm having a priority queue as 0, 1, what I can see is I have to check the graph, right? So from 0, 1, my initial values will be 0. Okay, But when I'm moving to the priority queue, which is 2, so in the priority queue, what we are going to store is the distance, comma the node, okay, the node and the distance value. So for example, node 2, say for example node 2, what I'm going to get is node 2 has 2 comma 1, right? So node 2 initially, node 2 has infinite values, okay, but node 2 is linked to uh, node 2 is linked to 1 and 3, okay. So node 2 is linked to 1 and 3, but this node 2 has some distances. So distance to reach 1 is 2, and the distance to reach 4 and the distance to reach 4 is and the distance to reach 3 is 4, okay. Distance to reach 3 is 4, okay. So what I can figure out is I have to update from 2 to 1. When I'm moving from 2 to 1, what is my distance? So my distance will become from infinite it will become a 2, okay. Similarly, I'm going to 3, so my distance from infinite will become 4, okay. So this is how we calculate. Now next, another node, let us consider the node 3, okay, the node 3. So if we consider the node 3, the node 3 has the distances 3, 4, 4, 2 and 1 and 5. So I will just check. 3 is connected to 2 by a distance 4. 3 is connected to 2 with a distance equals to 3 is connected to 2 with a distance equals to 4. 3 is connected to 5 with a distance equals to 1. 5 with distance equals to 1, and 3 is connected to 4 with a distance equals to 3, with a distance equals to 3. Now what I am going to update? I am going to carefully update the values. So from going from third node to second node, I am getting a distance as 4, but I already have 2, so which is lesser than 4, so I don't need to update it. I will keep my shortest distance, okay. From node 3, when I'm going to distance equals to 4, I'm getting a distance as 3. I'm getting a distance as 3. So in this case, I'm going to check, okay, I'm going to node 3. From node 3, I'm going to get a smaller distance, which is 3, right? I'm going to get a smaller distance, which is 3. So I'm going to update it. From 3 to 5, I'm getting a distance equals to 1. I'm getting a distance equals to 1. So I'm going to update it, okay. Similarly, I can check for the other nodes. So node 2, 3 done, and similarly I'm going to update my priority queue as 3, 4 and so on. So while we understand this particular problem, I would like you guys to see the code of this particular problem and help us with this, okay. So say for example, this is the code, okay. Initially we are going with the class solution, okay, and we are getting an integer of shortest path. We are taking these weights and the vertices, number of vertices, number of weights and the edges, okay. We are storing the adjacency list, which I already showed. Now we are populating. First we are pointing u equals to edge of I and 0, which is the start of the edge I and 1, which is the end node of the edge, okay, and w of edges is the weight of the edges. So in the adjacency list we are passing the add edge u to v. We are calculating the distance u to v with a weight w. Similarly, we are adding edge v to u with weight w, since the graph is undirected. Means there is no particular direction we are going to follow. Now we are applying Dijkstra's algorithm. We are having a distance array to store the shortest distance. We are filling the arrays with infinity. So integer.max value actually fills it with infinity. Distance equals to 1 equals to 0, the starting node as 1. Now array to store the previous node in the path as -1. We are filling the previous node as -1. Now we are having a priority queue, which is used to process all the current shortest distance, and we are adding with the starting node with the initial distance as 0. Now with the same way we are going to traverse. And current equals to, if we are getting the node with the smallest distance, as I already told, node equals to current dot 0 means the first node, and current distance equals to current once means the current distance to this particular node. And we are having an if condition. If the current distance is greater than the distance, then which means that if this distance is not the shortest, we are going to skip it. We are going to again continue. So for that we have the neighbors. We are having a single dimensional neighbor in the adjacency list, and we have a neighbor node and we have an edge both. If a shorter path of the next is found, which I already told, particular weight plus the node is lesser than the next node, then we are going to update the shorter path to the next node, okay, and previous node for the next node. So in the previous node, we are adding the node, okay. Lastly, we are adding the next node to the priority queue. If no paths are found, which means the value is still infinity, we are going to return -1 and reconstruct the path from 1 to n. We are just going to, it's like making the complete list. So we are having an iterator which is starting from n and which is till not it becomes -1, and previous as add, we are going to add the path in that list, reconstruct the path from 1 to n. Finally, we are going to reverse the list to get the correct order from the start. Okay, and lastly, we are going to add the total width to the beginning of the path and return the shortest part with the total width. So this was problem of the day, and I hope you could understand this particular problem. Thank you.